So I thought I'd do this in context, so I've got a specific example here. So this is something that I'm interested in. Some of my research is in metallurgical extraction by benign processes. This, what you're looking at, is a billet of titanium. To give you a sense, you can see the stairwell back here. So this is about 4 feet, a little over a meter here. So you can see this is one honking big piece of titanium. This came out of the primary reactor, the Kroll reactor, and then this is subsequently swaged and hot worked and so on to form these billets. So this is the first step of turning dirt into metal. That's called titanium sponge. And titanium sponge occurs inside a Kroll reactor. It occurs inside a Kroll reactor, which was invented by a man of the surname Kroll in Luxembourg in the 1930s. And then with the advent of World War II, he decided to be smart to get out and ended up in Oregon, where he became a professor. So he's known as Professor Kroll, although the truth be told, he really made his discovery before he became a professor. But he's still a professor, and so we'll honor him. And so the Kroll process for making titanium centers around this reaction. Here's the reaction written according to the rules above. We take titanium dioxide, which is found in the earth, and by some prior chemistry converted to titanium tetrachloride. And in a reactor that I'm going to show you in a moment, we react titanium tetrachloride with magnesium. Magnesium has a higher affinity for chlorine than does titanium and steals the chlorine from titanium to form magnesium chloride, leaving behind titanium metal. Now, we have to have conservation of mass. So you can see I've got 4 chlorines on the left, but only 2 chlorines on the right. So I'm going to put a 2 here and double the magnesium chloride. But now I've got 2 magnesiums on the right and only 1 on the left. So I'll put a 2 in front of the magnesium. And now we have a balanced equation. We have a balanced equation. And here's what the reactor looks like. You can imagine a giant vessel with a pressure seal on the top and a couple of valves big enough to make this. So this is about 15 feet by 30 feet. And so we introduce titanium tetrachloride, which is a gas, and magnesium as a solid and heat to 900 degrees C. And at 900 degrees C, if you look on your periodic table, you'll know that magnesium melts at 650 degrees C. So you have a liquid sitting here, titanium tetrachloride here, and this thing is sealed. It's called a bomb reactor. Nothing can get in, nothing can get out. And the pressure builds up here, and right at this interface, the titanium tetrachloride reacts with the magnesium according to this reaction. Now, this is very interesting. It's a beautiful reaction because titanium tetrachloride is a gas, magnesium is a liquid. Magnesium chloride is a liquid, but it is of different density and it's insoluble in magnesium, and titanium melts at 1670 and it's a solid. So what happens over time is this. The magnesium chloride that forms pools underneath the magnesium liquid, gets out of the way so that we can continue to keep this interface clean and have the reaction proceed. You don't want a reaction where reactant A reacts with reactant B, makes a product that covers the interface, and now the product is in the way of future reaction. So this is very elegant because I don't need any fans, I don't need no propellers, nothing. By density, the magnesium chloride settles and the titanium settles, and it's sitting here at the bottom. And you can imagine if we do this long enough, this titanium at the bottom will continue to build until it looks like this. As long as you keep feeding TiCl and mag. See, I'm talking metallurgical now. TiCl and mag, that's what you make. All right? So that's how we make titanium, first step, and so on. So suppose you get hired, and it's your first day on the job, and you're working at Cambridge Titanium, and they say to you, well, let's put in, the boss says, well, let's put in 200 kilograms of TiCl. We put in 200 kilograms of TiCl, and we'll put in 25 kilograms of mag. And the question is, what is the yield? What is the yield? How much titanium are we going to make? Well, you say, well, just multiply it out. But first, you have to see if things are in balance. We have to study the stoichiometry of the reaction. Stoichiometry, what does this mean? It's from the Greek stichios, which has to do with measurement, proportions. So if these are not put in to the reactor in proportion to what they are in the equation, we're not going to get the yield here. So first thing I got to do, this is in moles, this is in kilograms. So I have to convert the kilograms to moles, and then maybe I can make some sense of this. So if I divide by the atomic mass of titanium, 4 times the atomic mass of chlorine, and convert, I will discover that I have 1,054 moles of TiCl, and I've got about 1,029 moles of magnesium. Well, this equation says I need 2 times the amount of titanium tetrachloride. Well, it's obvious to the naked eye. 1029 isn't 2 times 1054. So I've got a problem here. I'm not going to get as much titanium as I put in titanium chloride. This yield is going to be restricted. It's going to be restricted by, this is sort of the chain is as strong as its weakest link. The yield is restricted by the amount of limiting reagent, and in this case, magnesium this is less than 2 times the mole number of titanium chloride. So this means this is the limiting reagent. The limiting reagent. All right, so now if we use that principle, then I'm only going to get as much titanium as I had magnesium, and you can see from the stoichiometry here, if I've got 1029 moles of magnesium, I'm going to have half of that number of titanium. So therefore, the amount of titanium is equal to 515 moles of titanium. And you notice I'm not worried, I'm not obsessed about significant figures and so on. I mean, it's a metallurgical plant, you know. To half of 1029 is 515. Is it 514.5? If you wish, I don't care. So 515 moles, and then I convert that, which gives me 24.7 kilograms of titanium when I use that amount of magnesium. And if you go to the text, section 2.7, you'll see the nuts and bolts of how to run these reactions. For those of you who had a lot of chemistry in high school, I know this is a review, but I want to bring everybody up to the same page, so we're starting with this.